Good afternoon, this is Schweitzer, and we're going to run a little video here on making decisions as far as intermolecular forces are concerned. Not everybody has the same decision tree. This is a decision tree that I use. Sometimes I use it differently. You need to decide how you're doing it, but you should still be able to function with this decision tree. So, with that said, I'm going to run through just a couple different examples. You could pause the video. And we want to see how this, this is going to work relative to AP questions and how you go about answering AP questions using a general. This decision tree just happens in your brain as you're thinking about different data that they provide for you. So, first things first. Again, this is a generic one. What type of sound is this? This might be something that that you maybe don't even know you're thinking about. Okay, so never covalent. This is one where, a bulk crystal of covalent bonds, like a diamond, and covalent bond is broken. Ionic bond is broken. What do we do here? Size of charge, internuclear distance. So these are talking points that if you're on a test, you have to talk about these. These are things that they're going to have a rubric discussing these things. Okay. All right. What if we're molecular? Okay. Now again, I tend to look for a highly electronegative atom: nitrogen, oxygen, fluorine. This is going to give me a significant dipole. Again, how you want to organize it in your brain, that's fine. But this is going to open me up to things like dipoles that are going to be giving me significant dipole, and hydrogen bonding, if that's how you want to look at it. But again, anything here, do we have a dipole moment created? A significant dipole. So any time we look at this, we're going this way as far as dipole moments are concerned. So I might say this might be instead here, is there a dipole moment? Okay, yes, dipole created, no, nonpolar. So if you have a dipole moment, that's one difference you could choose to do here. No. Okay, well then we have only London dispersion forces are broken when we melt it. Okay, we are non-polar. That's really important for solubility especially. More electrons, longer chains. And again, I could star this because these are talking points that you would need to discuss. You would need to discuss. You wouldn't want to leave that go without talking about those. And of course, our term here is polarizability. If you have a dipole created, is it a significant dipole? Significant dipole. Meaning, if you have data, is it going to be that this is going to be affecting it? Well, one of these guys here is really what we're looking at here. Hooking to a hydrogen will push us through hydrogen bonding, or just some other atom. So if it's hydrogen, then it's going to be hydrogen bonding, or just a dipole attraction. Okay. So that's kind of what we're looking at here. I'm going to walk through what I think some different options are. I don't know what that page is. Just an empty one, I guess. Alright, so we're just posing some information here. Now, I could give you this guy, and maybe eventually I'll swap this out for actual data. Melting point data, boiling point data, and that would be much more representative of what we have here. But I'm giving you just information. Said this is a gas room temperature, this is liquid room temperature. Why? Okay, let's walk through this and highlight some talking points. And you need to discuss both items on a test. Okay, so let's walk through CH4. It's molecular. Does it have a dipole moment? And the answer is no. Okay? Dipole moment. That's how I'm going to kind of look at this moment. And the answer is no. And it's and why? It's symmetrical. Alright, and that I'm going to start as a talking point. Therefore, London dispersion forces is something you want to talk about, and more electrons and longer chains. Every star is something that they would likely have a talking point on. Okay, the other guy, CH5. Okay, let's do this one in different color. Alright, it's molecular. Is there a dipole moment? Not really. CH5 is fairly symmetrical. If it has a dipole moment, it is going to be almost next to nothing. Okay? So we're going more towards London forces. Of course, longer chains is really what we're looking at this guy. The first one, longer chains really wouldn't be included because there aren't any longer chains. So the talking point for the CH4 would be the fact that you have very few number of electrons. So this would be very small. And this is going to be very large. Okay, so this conversion point is comparing these two right here. They both have the same intermolecular force. One has a very small amount of it, the one has a little more because of these factors. Alright, water, H2O is a liquid. Carbon dioxide, H2O is a gas, or CO2 is a gas. Okay, sketch it out. Now, again, in your mind, we want you to kind of walk through this. I just did this on the other one, and of course we could add that in there. I don't know if I have that here. I do. Okay, I do. Okay, so we'll add this here. What are my thought processes here? And I'm going to let you sketch it out here for a moment, and then I'll walk it through and I'll highlight it. So take a break. Try it out. Alright. So for this guy, let's do blue. We'll do the CO2 in blue. So first of all, it's molecular. Do we have a and again, they're saying steel here. You could sub in dipole moment if you would like. Yes or no? I don't have a dipole moment because I am symmetrical. Therefore, what do I got here? There's any long chains. This is a talking point right here. Okay. Next guy. Let's flip over to a different color. All right. H2O. So, do I have a dipole moment? Yes. Dipole is created. Is it symmetrical? No, it's not symmetrical. So I create a dipole. Do I have one of these guys? Yes. Hydrogen bonding is a talking point. Alright, this guy. Take a moment, pause it. What do you see here? Alright, next up. Let's do red. We'll do the Al2O3, ionic compound, metal, non-metal, size of charge. This is the talking point for this guy. It's got +2, +3, internuclear distance. Let's see what the other one does. I'm comparing these two items here. Carbon diamond. Okay. In this situation, I have what type of substance? It's network covalent. So what bond is broken is the covalent bond. Alright, much stronger bond. So I'm going to really be comparing this item to this item. I don't really need to talk about size of charges here. This is the talking point comparison between these two. One's breaking covalent bond, and one's breaking an ionic bond, and that's really the difference in the situation. Alright, CH4 and C3H8. What does your decision tree look like? Go ahead. What are your talking points? Alright, here we go. Let's do CH4 in blue. It's molecular. Does it have a dipole moment? And the answer is no, because it's symmetrical. So it's nonpolar. And in this case, CH4 is going to have, well, not much. Alright, we got to talk about this guy. It's got electrons. It doesn't have that many electrons. So this is all it's got. And it's small. So not a lot of LDS for this guy. here we go, in red is going to be the C3H8. Again, molecular. Is there a dipole moment? No, it's nonpolar. We have length-weighted forces that are broken, but we have a little bit longer chains. So this is the two talking points that we would want to discuss with these two guys. This guy might be a little larger because of the longer chains, more polarizable. Okay. Water is a gas at 100, but NaCl is a solid. Take a moment. What's your decision tree? What are your talking points? Alright. I didn't add one in here. Okay, let's just do this thing on the fly here. First things first, NaCl is ionic. Okay, this is NaCl. But the other guy here, the water is molecular. So what are my talking points? Well, in this case, in water, it's going to go water. This has a dipole moment, so we're going to eventually go to hydrogen bonding. Alright, so this is what's broken when you melt this guy, the water. But in ionic compounds, we're breaking an ionic bond. This is a much stronger bond. Therefore, it takes more energy to melt. So at the current 100 degrees Celsius, not enough energy to break this bond. Yet this weak internal force is broken. Alright, take a moment. Read over, see what you think. What are they describing here? And in this situation, there you go. It's describing a network covalent bond. Typical question. Alright, and we'll stop there for our just discussion of internal forces and how we apply it to states of matter.